Basically, it's something about ordering the real numbers, is that right?
Yeah.
Yeah, so I talked to my brother about that. And so to suppose that there's a next, to find a successor function for the reals basically amounts to, essentially, if you could do such a thing, you'd be able to show that the reals are countable. In other words, their bijective corresponds to the natural numbers, but you certainly can't do that. On the other hand, maybe the next best thing would be, suppose you have a set of real numbers and you could find a smallest thing in that set. So you could perhaps say, maybe there's some way to take the real numbers and give them an ordering such that they have the well-ordering principle. In other words, that every set bounded below has a smallest element, has a min. That you actually can do. But here's the thing, it's like, well, how do you do it? It can basically be shown that it's not constructible, not possible to actually do it in terms of the sort of constructions we do in here, let's say, to be made. So it's an interesting question you asked, but you basically answered no. So. But anyway, yes, as soon as I told Bill, my brother, half of your question, and he just started rattling the stuff off. And then, because he spent some months considering foundations of math and things. Things that I'm not, I don't have as much of an appetite for in my existence. All right, so I'm going to talk about some of the proofs from section 6.1 and 6.2. I'm going to do a lot of pointing in here. So we'll do some writing. But oh yeah, funny how that works. Oh, there. Okay. So section 6.1 is on the triangular form. When is a linear transformation? I will post these guys. So, and I'm really doing a little more here than writing out the textbook in my own words. Not really made my own words either. I mean, it's mostly just their words. Which, by the way, many of those words seem to also be found in Serge Lang's linear algebra, which is a classic. Anyway, so we say that T, a subspace of V is a T invariant subspace if the image of W under T is again a subset of W. So T invariant subspaces are really important. Just to, sorry guys. So before I get into this though, what are some examples of T invariant subspaces? So if I have T a linear transformation from V to V, there's two really stupid obvious ones. How about this? T of 0 is equal to 0, right? So that says that T of the 0 map. So 0 is an invariant subspace. How about the range of T? Well, by assumption, T maps into V, right? And we proved before that that's a subspace, right? So well, anyway, it's a subset of V. So V itself is an invariant subspace, kind of silly. Another thing you could check, E lambda, which was what? That was the kernel of T minus lambda I, right? You can prove that this is an invariant subspace. So for lambda an eigenvalue, so what would you? Well, I guess if lambda is not an eigenvalue, what are the two cases here, really, by the way, guys? Either this is just 0, if T minus lambda I inverse exists, right? Now the inverse of that existing, what would we capture the inverse of that existing by what? That would be the same as, in terms of determinants, we could have the determinant of T minus lambda I is not equal to 0, right? That would be that. And I guess technically speaking, sorry, really guilty. Europe. And on the other hand, it's just got eigenvectors, right? set of eigenvectors with eigenvalue lambda. If the determinant of t minus lambda I is actually equal to 0, right? So I mean, either the determinant's 0 or it's not for a given lambda, right? So either you've got an honest to goodness genuine eigenspace, which is non-trivial, or you got the trivial space. Those are your two options. But in either case, of course, if it's 0, we already know it's an invariant subspace. If it's a genuine eigenspace, then let's see here. If x is an element of e lambda, right? Then t of x is what? Lambda x, right? So e lambda is a subspace. So certainly a scalar multiple of something in the subspace is again in the subspace. So lambda x is an element of e lambda again. And this shows you that t of e lambda is a subset of e lambda. So therefore, the eigenspace is t invariant. All right, so here's some examples. Like the fact that the eigenspace is an invariant subspace is really the most important for our studies. Okay, so now we have some sense of what it means to be t invariant. Let me get back to my slides here. I'll just turn off half the lights. I think we can still see it on the camera when I do that. So proposition. If you have t from b to b linear, and if you have a basis x1 through xn, a basis for b, then t is upper triangular. You'll allow me this abuse of notation. T is upper triangular if w sub I, which is formed by the span of the first I of these vectors, okay? So you can have I equals 1 gives you span of x1, I equals 2 gives you span of x1, comma x2, I equals 3 gives you span of x1, x2, x3, and so forth. If each one of those is t invariant. So t invariance of these particular subspaces is equivalent to triangularizability of your linear transformation. We say that the transformation is triangularizable if it's possible to choose a basis which makes the matrix of the transformation upper triangular. That language is completely consistent when we say t is diagonalizable if you can use a basis such that the matrix of t is diagonal, right? So, yeah. Oh, no. That's not a question, it's a grade. All right. So, let's just go through the calculation here. It's not hard. If you suppose that the matrix is upper triangular, what's that mean? If you look at the jth column, you can form it from sums from I equals 1 to j of the standard basis, right? That's just immediately obvious if you look at a triangular matrix, right? So something like this, etc. So like this is from the span of E1, E2, E3, right? And so that's the third column. You can build it from the sum of the first three, standard basis. Well, the same for the jth column. That's what it means to be upper triangular, right? But if the jth column of A, where A is the matrix of t beta beta, is that means that t of xj has to be formed from the sum of the first j x sub i's in the basis beta. Just working back through the coordinate map. Consequently, the image of the xj basis element is in the span of x1 through xj, or what we just call w sub j in the statement of the proposition. What does that mean? Oh, that means that t of x, that means that it then follows, right, that the linear combination of these guys is again in the span. But that shows, of course, that an arbitrary thing in w sub j is again in w sub j, which goes to show you that w sub j is a t invariant subspace. So upper triangularizability of the matrix for t implies the invariance of these w1, w2, wn subspaces. So we can trade triangularizability of the matrix for the invariance of these particular sorts of subspaces. Now, why is that interesting? Well, let's go on. We'll see why. So, and then the converse is pretty much the same calculation. I'm going to go on. So my philosophy here is to try to go pretty fast through the proofs that I don't think will help you much with the homework, right? But I feel like I should say something about them. So I'm going to try to hope, if I keep talking at a reasonable speed today, it should leave us plenty of time to talk about the calculations that you need to do and so forth at the end of today, Wednesday, and Friday. Anyway, so T is triangularizable if and only if there is a basis such that the matrix of T is ever triangular. I already told you that. And we just discovered that that's equivalent to basically finding a sequence of subspaces, W1, W2, Wn, which are nested. Now, I actually think this shouldn't be equality. I think it has to be proper subset. But, no. Well, anyway. I think those should be proper subsets. I have a typo there, okay? Now, here's a proposition which makes a decent test question. This one's actually not too hard. It's very calculational. This is a nice proposition and proof I will go somewhat slow through. Let T go from V to V, and let W be an invariant subspace, all right? Then the characteristic polynomial of T restricted to W divides the characteristic polynomial of T. All right, so I'm actually going to put this away and write this one out because it's worth doing now. Then we'll come back to my projector here in a minute. So here we go. Proposition 6.1.6. We have T going from V to V, and W, a subspace of V, with T of W, a subset of W. In other words, W is an invariant subspace of T. Then the proposition says the characteristic polynomial of the restriction to W, the characteristic polynomial of T restricted to W divides the characteristic polynomial of T itself. All right. So here's the proof. So what we do is we let alpha equal to x1, x2, about xk. We want this to be a basis for W, all right? Let that be a basis for W. And then extend that, all right? By, let's say, alpha prime, xk plus 1, xn. So what? So alpha union alpha prime equals to beta is basis for B. All right. Now, all we really need to do really isn't much to the proof of this. We need to use the invariance of W. What does that mean with respect to this basis? What is it? Let's let x be an element of W. Then what can we say about T of x? Well, T of x is an element of W as well, right? Because W is an invariant subspace, right? So the image of W under T is again in W. What does that mean, though, for in terms of a formula for T of x? So I can write it in the span of what? The span of alpha, as we've defined it, right? So there have to exist constants. So they have to exist constants like A1 x and oh, sorry, I seem to have forgot a sub j. So we need to put a sub j on the x. I really want to argue for a basis element, so just a little bit more cluttered here. There's a j here, and there's a j here. I'm looking at the, 1 less than or equal to j less than or equal to what? K, right? So this has to be equal to something like A1J x1 plus A2J x2 plus da 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 plus A, K, J, X, K. Because it's in the span of alpha. Right? But just to be a little bit more blatant about it, plus what? Plus how many of xk plus 1? It's 0 xk plus 1, right? 0 xn's. Right? But this informs us what this implies, you know, what the jth column in T beta beta looks like, right? It says that that jth column only has non-zero entries in the first k rows, and it has 0 in the last n minus k rows. I don't really care what happens with the rest of the basis. The point is, from this calculation alone, you can see that the matrix for T has to have a very particular pattern. So the matrix of T has to look like this. This follows from what we just calculated. It has to look like A, then there's a B here, there's a C here, I don't really care what those are. There's a 0 here. So this is a K by K block. Okay. In particular, observe that if you take T and you restrict it, we take T and we restrict it to W, right? What's T restricted to W? T restricted to W of X is equal to what? How do we define this? What is the restriction of a map? Yeah.
Is it T maps to W?
What's the I wrote a formula. T restricted to W of X. What is this equal to? How do you calculate the restriction of a map?
Would it be using only?
Yeah, using only what? There's
Well,
only
anything from the, it's like the span of the basis alpha.
no. It's much simpler than that. The only thing it can be.
Because Albertson.
I'll save you guys. T of X. It's just T of X. I'm fishing for the definition of restriction. Restriction says you use the same formula for the function on a smaller domain. That's all. And well, I guess we also, in the case of this, there's a little bit more to it. We also assume that the codomain has been modified to W as well. And the reason I say that is because we shortly thereafter write, and the matrix of T restricted to W with respect to the alpha basis. You see alpha is a basis for W, right? That's just what? Basically ignoring the green stuff here, just looking at the red, it has to be the same. Anyway, all the things you guys are about to start saying are far more interesting than the things I just wrote. Okay? I'm not saying anything terribly profound here. It's really just a question of notation of what we mean by restriction. Okay? So if you don't follow right this second, don't be too bothered. The point then is, what's the characteristic polynomial of T? Well, the determinant of T minus lambda I is what? It's the determinant of A minus lambda I, C minus lambda I, where to be more descriptive, this is the K by K identity, and this is the N minus K identity, right? But thankfully, happily, determinants of a block diagonal nature have a very, very nice identity, which is just that this is the determinant of the upper block times the determinant of the lower block. All right. And that proves the theorem. You see, because this on the left-hand side is the characteristic polynomial for T. This right here is the characteristic polynomial for the restriction of T to W. And that proves that that characteristic polynomial divides the characteristic polynomial for T. Okay, so you're like, well, one polynomial divides another. What do I care? Well, operatively, what we really care about here is that they have to share eigenvalues. So the restriction, right? If the characteristic polynomial for the restriction factors right, into like lambda minus lambda 1, lambda minus lambda 2, blah, 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 then all those eigenvalues, lambda 1, lambda 2, are also shared eigenvalues of the parent mapping, the big mapping T. So we can discover the eigenvalues for the larger map T by studying its action on invariant subspaces, right? Any eigenvalue we find with respect to the restriction to an invariant subspace has got to also be an eigenvalue for the whole map. And that's very nice, because we could take a 20-dimensional map and look at a 2-dimensional invariant subspace, then we're doing a 2-dimensional calculation as opposed to a 20-dimensional calculation, right? It's really nice. Divide and conquer.
With that, I don't know if you ever said that, but like, you know how we have like the like change of well, the base like T restricted W to alpha alpha. Like, you know how it's a really big matrix with things along the diagonal.
Yeah.
Like if you had, what you were just saying, like if you looked at one of the factors of it, and if you added all the factors together, would you get the initial big matrix?
Not unless they're, I mean, not usually, because there's also eigenvalues associated with this piece, which don't have to match up with that piece. So it's not the same as T. I mean, there's information which is lost.
Yeah.
Yeah.
But like, wow, so that's much well, never mind.
It's okay.
Really,
I think the proof of the next thing actually may kind of scratch the itch. There's something that you're starting to ask about that I think we'll get to. Yeah.
Where did the n minus k from? The lower.
Oh, so the dimension of V being n means that whatever's left over has to be n minus k. Yeah. Yeah. So I try to use n for the dimension of V. Now, the theorem that we're trying to prove in section, oh, I seem to have turned all the lights on again. The theorem we're trying to prove in section 6.1 is basically this: if T has dimension V roots over the field F, where F is the field over which the vector space we're looking, if your characteristic polynomial has n roots over the field we're considering, then T is triangularizable. That's the theorem. Now, we know already that all matrices are not triangularizable because we know about this example, right? In R2, you have rotation, cosine minus sine, sine is cosine, with theta not an integer multiple of the pi times the integers, rather, not pi, not a multiple, integer multiple of pi. The eigenvalues we calculated before were cosine theta plus or minus I sine theta. Well, those are complex. Those aren't in reals, so we have no hope of that being triangularizable. So there's, I mean, it's, that said, we also know that if we complexify, right, if we complexify T, in this case, then the eigenvalue, then it would be triangularizable, because in fact this matrix is diagonalizable over the complexes. It just has diagonal form I mean, it has cosine theta for the upper entry and cosine minus I sine theta. I mean, this can be diagonalized if we allow ourselves complex similarity transformation, but anyway. So, I guess my point was a failure for triangularizability could be worked around by simply enlarging the field to a larger field which is algebraically closed. You're like, well, is there always a field over the field I'm given which is algebraically closed and contains my field as a subfield? I don't know, you'd have to take 422. No, there is, but you have to take 422 to see that stuff. Okay. Now this is the, this lemma is technical, but there are some things to learn from this lemma, so I think it's worth talking about with you guys because there's really nice formulas in this lemma, if nothing else. The lemma is basically this: if we have a vector, if we have a linear transformation of T, right, and we have an invariant subspace W, where is it? Here, right, and W is not, it's completely invisible in the video. It's weird, right? Like, they'll think I'm just crazy and just waving around my arm. What am I doing? But anyway, so this right here, I guess I should probably use something that.
That's like the bonus of coming to class instead of watching on video.
Ah, yes, I should. I mean, there are many other reasons, but it's here. So the W is not the whole vector space, okay? That's what I'm trying to say there. If that's an invariant subspace, then what you can pick an X which is not in W, and if you take W plus the span of that X, and not just any X, okay? A very particular X. Okay, it's not saying this is true for all x. What we're saying is we can construct an x, a very specific x, such that w plus the span of x is still t invariant, right? But that's going to give you this like sequence of subspaces, right? Because you can take a small subspace, find a vector as a very particular vector outside the space, such that x plus the span of the vector. All of a sudden, you've got a subspace which is a little bit bigger and still t invariant, right? So this lemma is going to allow you to build a sequence of subspaces, each one of which is t invariant. And consequently, that's going to build for you the basis which makes T triangular. I mean, that's a sketch of the argument here. So how do we prove this? You take a basis for W, like we did before. I'm using the same notation. And you define a mapping P, which is essentially, it's the projection mapping we did before, except there's no assumption of perpendicular or anything like that here. We just take P equal to this. So it takes, and it just kills everything that's beyond k. So k plus 1 to n dies. So it's immediately obvious that in the kernel of this mapping is the complement to w, right? The w prime. And w prime being formed by the span of alpha prime, okay? Yeah, everything's not in w. So the kernel is w prime. The image of p is clearly w because you can take anything in w and get to it. It's immediate from the formula. And you can also calculate that p squared is equal to p. All of these properties were also shared by our orthogonal projection. What's the difference between an orthogonal projection and this more general sort of projection here? There's one thing we don't get. It's no longer true that v is equal to w. I don't think it has to be true this anymore. Well, it might be true. I don't know, but they don't have to be perpendicular. So there's something lost here, but probably get a favorites that if Bailey had a chance to document.
Could you say that w prime doesn't necessarily equal w perp?
Right.
Okay.
Yes. So you could have, like, two-dimensionally, w could be this, w prime might be that. Right. So you could have E1, let's say E1 is w, span of E1 is w. You have like E1 plus E2 is the thing that's spanning w prime. So they could be skew lines, for example. But anyway, you can also look at I minus p, and I minus p basically plays the same role for w prime as p did for w. Because the kernel of the image of I minus p is w prime, the kernel of I minus p is w, I minus p squared is I minus p. It doesn't actually use that in the proof, I just thought it was fun to notice. Sorry. That's actually a digression. So then he defines this mapping S, and S is equal to I minus p composed of t. All right. So you notice that the image of I minus p is w prime, which is the span of alpha prime. But that then, so if this is in w prime, if I take things, I feed them to v, and then t of v goes into this, that means it's still in w prime, right? So in other words, the image of a composite is pretty much governed by the left factor in the composite. That's something I don't think we've proved yet, but would make a great quiz 3 question. Yes?
Now, does IM mean image or
Image.
the imaginary part?
Image. Yeah. Oh, good question. I usually do, in my defense, I usually do this for imaginary, and I would do this for image of v. Although technically speaking, I kind of like this more because it's t of v. Yeah, that's actually what it is. But yeah, some people write range. I'm just following the book here. He uses dim for image.
Yeah, and I think he also uses it for imaginary.
Yeah, probably. There are worse things. We need more letters. Oh well. We can't all be Chinese. Let's see here. So, where was I? Yes. So the image of S is a subset of W prime. And you can see that W prime is actually an invariant subspace of S, because we just said that S of something is back in S of something in V is again in S. So that means S is an invariant subspace. Excuse me, W prime is an invariant subspace. Excuse me, I will eventually get this right. If you pick something in W prime, right, that gives you T of V. Well, T of V doesn't have to be in W prime, right? But this puts it back in W prime. So it follows then that S has W prime as an invariant subspace. But what does that mean? That means that S restricted to W prime, the characteristic polynomial of that divides the characteristic polynomial of S, right? And if you look at T being this, you can argue that T restricted to W is A, like we did in the previous proposition. But S restricted to W prime is the C, as it turns out. And so basically it then follows that S also has to divide the characteristic polynomial T, which means that the eigenvalues for T are also eigenvalues for S, which means then that I have a solution to this equation here, I minus pt of x is equal to lambda x. But that means that this is equal to that, and then I get t of x is equal to lambda x plus p of tx. But you see, I know that p of tx is in w again, so what do I have? I've got something lambda x plus something in w. It follows that this x is specifically the one I referred to in the theorem that we can enlarge the invariant subspace with. Now, if you didn't follow what I said, I wouldn't be surprised. I had to read this about 3 times before it finally penetrated my thick skull. But it's a standard argument, like I said, you'll find it in other books. But this is a kind of technical argument, I would say. But I like it. I mean, it's interesting. So what? So that allows us to prove the triangularizability. T from B is linear map, then T is triangularizable if only if the characteristic polynomial T has dimension of V roots in F. And I think you guys are already a little bit worn out, so I'm going to skip the proof here. So it then, because of the way the proof went, that proof that I just skipped, it basically, you could start with any eigenvalue. You can basically do the proof in such a way that you can order the eigenvalues. So it turns out then that we can always take a triangularizable T and find a basis such that we order the eigenvalues, the first m of one of them, the second m two of them. So these are repeated, but like I could take the first ones, the second ones, the rth ones, I can put them in order like that for the triangular matrix. And I still don't have any control of the things above the diagonal, but that's a start. That leads us to the Cayley-Hamilton theorem. If T is a mapping from V to V, linear, finite dimensional vector space V, P of T is the characteristic polynomial, then we can show that if you plug in T, the transformation T into the characteristic polynomial, we get back to zero transformation. And the proof here is it's actually pretty easy to understand. It's basically relying on the theorem we just proved, which is that if you have this, I mean, we're going to prove it in the case that all the eigenvalues are in F, right? If all the eigenvalues are in F, in other words, if the characteristic polynomial has n roots, then it follows that there's a basis, like we've been talking about today, such that the matrix of T is triangularizable, right? So let's just walk through it here. So if all of the eigenvalues are in F, that means you can factor T, P of T, the characteristic polynomial like this. Some people would say that means that the characteristic polynomial is split. It can be factored into linear factors. These could be repeated, but the point is there's n of them. Okay? And then to show that that is zero, when you so what is P of T? P of T is you take this polynomial and instead of putting this variable T, you put the transformation T in place of little t, right? And the subtraction by lambda I, lambda 1 is just understood to be multiplication by like lambda 1 times the identity operator, right? It's the natural change the polynomial to a corresponding matrix, a corresponding transformation of a matrix. So that to show that that's zero, if I can show it's zero on a basis, that works, right? So to start with, notice what it means for the basis to be for the matrix to be for T to be triangularizable. It means that we have this basis such that T of xi is equal to lambda I xi. That's the lambdas on the diagonal, and then plus this other piece. And the other piece is built from everything else that's coming before xi because it's above the I from the diagonal. So it's in y sub I minus 1, which is basically a span of x1 through xi minus 1. It's in there somewhere. And the w sub I minus 1 is I denoted at the start of today against lambda.
If T was like perfectly diagonalizable, that there would be no y on that small part? Is that correct?
Yes.
Okay.
Right. If t is, one way of saying that t would be diagonalizable is if we could make all of those y's be 0. Yeah.
Okay.
Right. That may or may not be possible. But when you feed p of t, x1, what do you get? Well, here's the cool thing. This factorization, the beautiful thing about all these factors, these are operators which commute with each other. So we used this before when I talked about the linear independence of k eigenvectors. We had a product of operators that I could commute, and I showed you that you could commute them because they're equal one way or composed one way or the other way. I actually went through that. Or I waved my hands about it before. Now I waved it twice. It counts. So once hands are waved twice, it's legitimate proof, right? But so if you take the copy here with lambda minus 1, you move it all the way over there, as you can do because these commute, these factors, t minus lambda j. Then this on x1 is 0 because t of x1 is lambda 1x. So when you feed x1 to this, you get 0 minus 0, which is just 0. But when you feed 0 into this linear transformation, 0. So there's 1 down. Now what you do then is suppose inductively that you've showed that p of t is equal to 0 for all I less than or equal to k. Here's an example of strong induction. Landon, I was looking for one for you. Here's an actual strong induction example. So I'm going to suppose that we have shown that p of t is equal to 0 for all I from 1 to k. Then we're going to look at k plus 1. All right, so x k plus 1, what I do is I just reorder the factors. So I've got all the n from like n minus 1 at the front of it. And then I've got my k all the way down to 1 here. And I just put the k plus 1 over here because I want that to hit this first. When that hits xk plus 1 by construction of the basis, t of xk gives me lambda xk plus 1 plus yk, right? So then this piece cancels with that piece. And I'm just left with, after the first evaluation, all of this is just yk. So I'm feeding yk into the product t minus lambda 1 all the way down to t minus lambda k, right? But by construction, that's 0 because I've already shown that. I mean, I'm assuming inductively that p of t is 0 for up to k. So the induction hypothesis shows that that product on yk is 0. Consequently, by induction, the p of t on the basis is 0, and then it follows that the operator itself is 0. This is the Cayley-Hamilton theorem, which says simply this, that if you plug the transformation into the characteristic polynomial, that gives you the 0 transformation. It's a very useful fact, theoretically. Computationally, I don't know, not so much. Anyway, questions about, well, if you found an error in my proof, tell me after class. It's too sad. Nilpotent maps. All right. So section 6.2 is about nilpotent maps. What is a nilpotent map? Well, let me put the projector away and write for a while for the rest of class. Just for a little bit. Yes, I did.
Okay, so you know how you have like the t, the base, like or whatever basis to the basis that matrix. That's so like if it's diagonalizable, and that means each column like corresponds times like a element of the basis times a coordinate scalar or something like that.
We proved before
Yeah.
that t is diagonalizable if and only if there exists an eigenbasis for t.
Yes.
So.
And each one of those columns kind of corresponds to that, right?
Right. I mean, if this stuff we're doing right now, if t is diagonalizable, these subspaces, well, let's say it.
Well, what
I mean,
But I was going to ask, like, the y part, like I asked, that's needed if you need to add something extra to the basis, right?
Right.
It's not enough. So
Yeah.
that's the extra part. That's like why we have those ones not the basis.
something like that. Yes. Oh, that. Okay. So the ones above it, that brings us to the next section. So
Okay.
now we don't have anything above. The first section 1 just gives you this triangular. It doesn't tell you anything about what's it look like above the triangle. But that's what the next section is about. The next section we study the nilpotent map. So, oops. So again, we let n go from v to v. And he argues basically if, so then if, and then such that n to the, let's say, n to the k is equal to 0, but, oh, I'm sorry, still wrong. Sorry, guys. Let's such that n to the n is equal to 0. Now, you know, a sufficient condition for that, lambda equals to 0, causes this. Why? Because if lambda is equal to 0, what does p of t look like? If lambda equals 0 is an eigenvalue for n, right? If n is an operator such that lambda equals 0 is an eigenvalue, that means that lambda itself, if I write p of t for my characteristic polynomial, so I've got like t minus 0 is one of the factors of it, right? And then I've got everything else. Well, I don't care what the rest of the thing is. Let's call it g of t. Oh, I don't want to call it g of t. That is something specific. P2 of t. Everything else in the characteristic polynomial, okay? So the point is, if you plug in n, right, then this gives you n n times, well, p2 of n, I suppose, is equal to 0. Now, p2 of n, I don't know what that is, but no, that's not the right argument. It doesn't really matter. Let me stop distracting myself. I mean, you could take that and raise it to the nth power. Of course, n to the n would have to be 0. Why? If n is the dimension of v, I'm still assuming that the dimension of v is equal to n. So the characteristic polynomial is what? It's order n, right? So,
Does it have to do with the last theorem that we went over, where the characteristic polynomial?
yeah, that's what I'm using here.
Okay.
I'm using Cayley-Hamilton here.
Okay.
So there's definitely something, some other polynomial of n, such that that times n gives you 0. Right? I mean, if you, well, anyway. I don't think I've given you a decent argument yet for that, but it's at the start of a stupid thing. I'm an idiot. Oh well. Nothing new. So n to the n is equal to 0, right? You can assume that for that for us is the definition of n being nilpotent. Let's say that defines n as nilpotent. Now, however, but I would caution you, not of order n. I've defined for you guys before, right, the idea of nilpotent of order, for example, 2. Like, I said this, I said if n squared is equal to 0, but n is not equal to 0, then n is nilpotent of order 2. Okay? So the order of n, like the order of nilpotence, doesn't really matter too much to me for this section. I think after the section's done, you can define it in terms of the technology that we developed in section 6.2, but there's no need just yet to do that, okay? So the point here then is, if we pick a particular x not equal to 0 in V, right? Then for some k, which is less than, I think it has to be less than n actually, yeah. For some k less than n, or I guess we could say less than or equal to n minus 1, that's probably safe to say, we have n to the k equal n to the k acting on x equals to 0, but n k minus 1 x not equal to 0, okay? So what does that mean? If you look at it, what would that mean? That would mean n times nk minus 1x is equal to what?
0.
Right, nkx, which is equal to 0, right? Which, by the way, is equal to 0 times nk minus 1 acting on x, right? But what does that, what does that make this thing here? Look at that. So therefore, yeah, say sure, nk minus 1x is a what? Blank with blank.
It is not one of those words. Matrix.
No. Yes. I'll take E vector with eigenvalue what?
0.
Right. That's what I was fishing for. So yes, that makes this an eigenvector with eigenvalue 0. Now that alone is not too exciting. But here's the really, really neat thing. We can argue then, it can be shown, you can prove the following. You can prove that nk minus 1x and k minus 2x, n of x, x. So this is a linearly independent set. That's proved in this section. All right. Hence, Cx, which is equal to the span of the above set. Has dimension k. So this thing I just wrote down here, this is the so-called, this is the k cycle generated by initial vector x. Okay, so what? Well, if you look at n restricted, all right, if you look at n restricted to C of x, this particular case cycle, and you look at the matrix of that, say alpha alpha, so that would be what? That would be like, you take n, let's see, what's the first thing? And I'm using the same ordering as right over here, calling that alpha, all right? So like, the first thing in the alpha basis is n k minus 1 x, right? So you calculate that thing, and then you calculate its coordinate vector with respect to the alpha basis. Then next, you take n k minus 2 of x. Calculate that with respect to the alpha basis, and so forth and so on. Eventually you get to what? N of x in the alpha basis. So what do we got? We've got the coordinate vector of 0. Right. This is what? This is the coordinate vector of n k minus 1 acting on x. And then the coordinate vector of x. Well, I can be more specific. That's actually what? This is the what? This is the k minus 1th element in alpha. So that means that this is actually standard basis member ek minus 1. Likewise, this is just equal, this just gives you 0. This is E1, because that's the first thing in the alpha basis. See, first thing in the basis, coordinate vector E1. And so what we have is what you're looking for, Landon. So this is where the 1s are coming from. And so this is the canonical block for a nilpotent cycle. What I'll prove next time, you guys, is that if we're given a nilpotent mapping, we can take and we can find a basis which is formed by stringing together R of these K cycles in such a way that we get a basis for all of the, which makes the matrix for n just the direct sum of these sorts of blocks. It's actually much easier than what I tried to do with this, what I did earlier today. The proofs in section 6.1 are actually far more technical. 4.2 is actually pretty easy, so we'll wrap it up next time, but I shut up. By the way, do pay attention to the link I gave you. For the next to last problem, you're asked whether these three matrices are similar or not. How do you tell if matrices are similar?
Well, you can find
Find a basis. Oh, you just try to solve. Yeah. Now, a very mean answer to that question is: are any of these similar? I don't know. Just look and try to solve this in general, right? Yeah. Go ahead. Solve that.
All right.
There's I don't know what, n squared. It's a, don't do that. It's bad. Don't try to do it directly. That's the wrong way. In that section where the problem is assigned, there's a theorem which says that two matrices are similar if and only if they have the same Jordan form. So the way to test whether those three matrices are similar is simply to find their Jordan forms and compare. As another more simplistic no-go theorem, if matrices have different determinants, or if they have different traces, then they can't be similar. But that's the sort of thing I'd like to talk more about next time. So I'm going to try to finish getting through the proof of the Jordan form Wednesday, so we still have a solid 2 days to talk about applications of it, which is really more what we're interested in. But, anyway, shut up. Oh, what I was trying to say is, you are free to use that website. I posted the link to find the Jordan form in that problem. There's 3 by 3 matrices. You can plug it in and it'll tell you the Jordan form. That saves you 5 pages of calculation.
He does have a hobby.
It really depends on what you're out.